Physics students, good afternoon. Mr. Fugit here. In this video, we're going to be looking at an object that is on an incline and how that object moves down the incline. Okay? So we're going to be looking at Newton's second law and how we can look at why the object is moving, okay? And kind of how fast it's going as it moves down that incline. Okay? So this problem is going to relate to one of the problems from your homework assignment number 6, which covers over forces in kind of a more advanced way. So the problem statement goes like this. A 2.54 kilogram block slides down a smooth, frictionless plane having an incline, of 30 degrees. The acceleration of gravity is 9.8 meters per second squared. Okay? So you're also given a diagram in your problem that looks a little bit like this. You've got your object. Okay? It is on an inclined plane of 30 degrees. You're also told that your object is a certain distance, and kind of up the plane. My value is about 2.69 meters. And it's just telling me how far up the plane I am. Okay? Now that's not going to come into play in this problem, but it will in kind of a future problem. Okay? We're also told the mass of our object, I'll write this over here, is a little over 2.5 kilograms. Okay? So what the question's asking us is for an acceleration value. And typically, when we're asked for an acceleration, we have to think really along one of two lines. Okay, one, are we going to use kinematics to help us get there? Or two, are we going to use forces and Newton's second law to help us get there? Now here, we don't have much information about velocities and times, right? We do have a displacement, a distance our object might travel, but we don't know really enough information to go that route of kinematics. So in order for us to find an acceleration here, we might need to use Newton's second law of motion. I'm going to write out here A equals something. Okay, we don't know what our acceleration is going to be. We just know we want to solve for it. Now, we've dealt with inclined planes over the last couple of weeks. And one thing that we've talked about is how we kind of redefine our coordinate system. Okay? What I'm going to do is, for the time being, I'm going to erase this 2.69 meters because we're not really going to use it here. Okay? And what we've talked about, one of the best ways to approach objects on an incline is simply by taking our coordinate system and tilting it to fit our new surface. So what we're going to do is we're going to call down the plane our positive x direction, and we're going to call straight up from the plane our positive y. We're just taking our coordinate system and we're tilting it to fit our new surface. And the reason why that's helpful is so that when we solve for this acceleration, it's now all in the x direction. I don't have to solve for acceleration in the x and the y. I can just solve for one value. Now that is going to mean that we analyze Newton's second law a little bit differently, but it's going to make calculating ultimately for our answer much easier. So what we'll need here is we'll need a free body diagram because we need to know something about a force that might cause this acceleration. So if you remember from what we dealt with inclined planes, we still treat gravity as acting straight down. We'll call this Fg. But remember the word normal. Normal we defined as meaning perpendicular. So our normal force is going to go perpendicular to our surface. So it's at a 90-degree angle from our surface. And we'll call this Fn. Now eventually what we're going to need to do is we're going to need to break our force of gravity into its components. There's going to be what we would call a y component of that force and an x component of that force. And if you'll remember, our block, according to our new coordinate system, it's only going to move in the x direction, what we defined as being the x. It's not going to move up off the plane or sink down into the plane, right? It's going to be moving along that surface, okay? Which is why we've called that our new x direction. So really all we're going to need to do here is figure out what force is causing it to do that, and then calculate for that force and use our mass to find an acceleration using Newton's second law. Now, we have an angle here, and one thing that we need to be able to connect in is how that angle is going to help us relate these sides of our vector triangle. This angle, 30 degrees, is the same geometrically as this angle up here at the top of our kind of our force triangle, if you will. And if you will notice at this point with our free body diagram, our force of gravity in the y direction, that's not causing us to move down the plane. It's just this component in the x direction. So that's where we want to focus in. We want to find the force of gravity in the x direction and use that to find our acceleration in the x direction. So I'm going to write out my equation for Newton's second law. Sum of forces in the x is equal to mass times acceleration in the x direction. Now, what I'll need is to figure out what force I have in the x. And if I look at my free body diagram, what that should tell us is that we don't just have a force that is solely in the x. We have this force of gravity that's kind of part x, part y. So, in my Newton's second law equation, I'm going to write Fg in the x is equal to mass times acceleration in the x. Okay, not all of that force of gravity is in the x direction. Part of it's in the y. So, we have our mass. We want to find acceleration. We just need to find that component of our force of gravity. That's all. Once we have that, we'll be able to find our acceleration. So I'm going to come to a new page and draw this vector a little bit larger. And here we've got our box. Kind of it's on its plane. And I've got this force of gravity. I'm going to draw this large so we can see it. Fg. Now that force of gravity has a y component and an x component. Okay? I'm going to call this our force of gravity in the y. And this right down here, our force of gravity in the x. And those just fit with our new coordinate system, right? We're no longer just horizontal and vertical. We're now at an angle, right? This is what we call our positive x. Here's our positive y. Now, we do know our angle, right? The angle that is between our force and this y direction, our angle theta, is the same as our angle of incline right in here. Okay? Now, for me, in my problem statement, that angle is 30 degrees. So I'm going to erase this and put in here 30 degrees. So I have an angle, and I kind of need to find one of these forces. What is just our force of gravity overall? Okay? And if you remember, our force of gravity, Fg, is just mass times g, our acceleration due to gravity. So our mass, we were told, is 2.54 kilograms. And the problem statement told us,
Jacob Bowen, if you are in the building, please come to the main office. Jacob Bowen, if you are in the building, please come to the main office.
Interesting. Usually aren't announcements this late, but we'll go with it. Okay? So we have our force of gravity is equal to mass times gravity. I'll plug this in. 2.54 times 9.8. And that force of gravity is going to be equal to, according to my calculator, about 24.9 a kilogram meter per second squared. That's what we call a Newton. So now I have my force of gravity overall. That's going to be this value right in here, 24.9 newtons. Once I have that, I'm going to want to find this opposite side. So I have an angle. I have what would be the hypotenuse, kind of my force triangle here. So I just need to use one of my trig functions. Opposite and hypotenuse, remember, SO, CA, TOA. So, opposite and hypotenuse means I'm going to use a sine function here. Remember, we also talked about when we introduced this, that finding that x component means we're always going to use the sine function for this specific scenario. So our force of gravity in the x is just going to be Fg, which we solved for, sine of our angle theta. And so Fg in the x, I'll take 24.9 newtons times sine of our angle 30 degrees. Do make sure your calculator is in degree mode, not radian. So that's going to leave us with our force of gravity in the x direction is equal to 12.45 newtons. So now we have our force. But remember, our problem statement was asking us for an acceleration. So we're going to take this force and plug it back into our Newton's second law equation that we wrote out previously. So let's come back here. Now we have our second piece, our force of gravity in the x direction. So let's plug in what we know. Our force of gravity is 12.45 newtons. That's equal to our mass, 2.54 kilograms, times our acceleration in the x direction. So, to find the value that we're looking for, our acceleration, we need to do a little bit of work here. Okay? I'm going to need to move this 2.54 kilograms to the other side. So, since it's multiplied, I'm going to divide by 2.54 kilograms. I'll do that on both sides of our equation. This value will cancel out. I'm going to plug in what's on the left side, 12.54 newtons divided by 2.54 kilograms. Okay? That's going to leave me with a value, my acceleration in the x direction, of approximately, looks like 4.9, and acceleration is meters per second squared. Okay? So it's a decently high number. Okay? But again, we have a surface that is frictionless, so that force of gravity is going to cause it to accelerate at a pretty high rate. Okay? So that should be how we can go through and find that acceleration. Remember, when dealing with objects on an incline, the main difference is that we're taking that coordinate system and changing it to fit our surface. Right? We want to try to get all that motion in one direction, okay? So that our acceleration is really one value, not two that we have to deal with. Okay? Your numbers are going to be a little bit different, okay? But remember, the process is going to stay relatively the same. So hopefully this will get you working in the right direction. Best of luck.